Okay, in this video, I'm going to do one more and last example of discretization. And again, we'll go back to what does that mean? We start with a continuous time state equation. This x dot equals f stuff up here. Where this u, the input, is zero mean unity white noise. And it could be a vector. X could be a vector, u could be a vector, f and g, matrices. That's what we start with. Discretization means come up with basically this discrete states equation. This x of k plus 1 equals phi k plus w. And that really amounts to the big things we do is find this phi. We have a formula for it. And we find this q, which is this covariance matrix of the input noise in the discrete version. And we have a formula for that too. And we're only going to consider f and g being constant. So here's our formula for that. So anyway, keep that page in your notes, and that's what we're going to use. We already went through the example I'm flipping through now. Here's the example I'm going to do now. We're given the continuous time state equation. We're asked for phi. We're asked for q, but we don't have to evaluate it yet. We at least need to find this integrand. And then part C is actually do find the off-diagonal terms of this Q matrix. By the way, Q is always symmetric. And this is from, I gave this as an exam problem one time. So you could do this during a timed exam, you know what you're doing. So A, finding phi. First we find this guy. Well, first we find SI minus F. So that'll be S along the main diagonals minus F. So nothing to adjust on the main diagonals. Minus 1 up here and plus 1 down here. Now we take that guy's inverse. For a 2 by 2, you need to know how to take the inverse of a 2 by 2 matrix. First, we divide by the determinant. It'll be s squared minus a minus 1, or 1 over s squared plus 1 up front. And then how do you do it 2 by 2? This guy, we switch the main diagonals, but in this case they're the same anyway, so you end up with the same. And then we change the signs of the off diagonals. This looks like we switched the off diagonals, but all we did was change, we kept them in place, but just switched the signs. Anyway, that's basic, some matrix arithmetic. Put that together, bring this back in. We have this, and every term in here translates into either a cosine or sine. So here's our phi as a function of tau. Here it is as a function of the time between samples, capital T. Here we are. We did part A. Part B. What we need to do is really find this guy, and the easier way to do it is do this little matrix multiplication, phi times g, and then multiply that result by its own transpose. So here's phi times g. So that's going to be sigma times cosine, it's going to be sigma times sine tau, 0, and then the sigma times cosine tau. Multiply it by its own transpose. I'll have sigma squared sine squared up here, sigma squared sine cosine on the off diagonals, and sigma squared cosine squared down here. So here was a sufficient answer for part B, or if you put it all together, here would be the integral you'd need to take if you needed to find the whole Q. Because this was a time test, I didn't want to see if they could do integrals so much. I said, just do the off diagonal, and they're going to be this it's metric matrix, so you only need to find one. So we find the Q12 term, which is the same as the Q21 term, which means find this integral. Sigma squared, and inside the integral is cosine sine or sine cosine. And hopefully you could have recognized this. You don't need a table or something to do this integral. You just call sine tau equal u, and du is cosine tau d tau. So the integral of u du is 1/2 u squared. In this case, 1/2 sine squared. And we just go from 0 to t. And when the argument is 0, the answer is 0. So we just need the upper limit part. And here's the answer to part C. And that's it. All we're going to do for discretization. Stop the share and end this thing. That ends this module on state space and discretization.